What we're going to talk about right now is the Markovnikov addition of water to a double bond. So as I've shown you before, I like to draw my wedges and dashes. And for this particular reaction, it's not extremely important because there is going to be a carbocation formed, but I want to draw them anyway just to make sure you're very aware of different groups. Okay. I'm not making this extremely complicated in the way it looks. This is going to be the alkene we're using. And the conditions that you're going to be looking for on the arrow will be an oxy acid. The most commonly used oxy acid is sulfuric acid. Okay? And this would be in water with heat. It would be important that this is dilute, meaning that there is a lot of water present in the solution. Water is a big component of this. And the reason that we care that there's a lot of water here is because we need water to act as the nucleophile. We don't want there to be any chance that it's the hydrogen sulfate anion that would be the conjugate base of sulfuric acid. It's also very important that you use an oxy acid if you want to do an addition of water to the double bond. And we're going to talk about that in some detail. But it is very, very important that you use an oxy acid. Some others that are commonly used would be potassium hydrogen sulfate. Okay, this is a strong acid. You might also use nitric acid or some other oxy acid. The point is you're going to be looking for a proton, and in the same compound there will be some oxygen. This is absolutely critical, and we're going to talk about it, but it has to do with the fact that the corresponding conjugate base has resonance delocalization of the negative charge. So because H2SO4 is a strong acid, it is going to be our proton source. Okay, now I'm not going to redraw my alkene in this fashion here for a second because it really doesn't matter if I have the wedges or the dashes in this particular reaction. We'll talk about why. So mechanistically, I'm going to draw out everything for a change. You are going to be donating a proton from the HSO4. Okay? Now, when an OH bond breaks, oxygen is the more electronegative element, so it's going to take both of the electrons in that bond to produce the proton. Once that has occurred, you need to have an electron pair donor. The electron pair donor is actually going to have to be either an electronegative element or a pi bond. And in this case, we do have a pi bond, but that's going to be the source of electrons. If you remember when we talked about hybrid orbitals, pi bonds are higher in energy than sigma bonds. So if a bond needs to break, you want to break the one that is weaker, or the one that would give you more energy. And this is going to be the pi bond. Okay? Now, I'm drawing it from the electrons, not from an atom. But you need to be aware as to which of these two carbons in the double bond gets the proton. You want to make the most stable intermediate possible. So this is why this is a Markovnikov addition. You want to give the hydrogen to the primary carbon, not the secondary carbon, because you would rather have a secondary carbocation over a primary carbocation. And again, that has to do with induction and hyperconjugation, which we've talked about previously. So once you have added that proton, you have a carbocation intermediate. Which in this case is secondary. Remembering our charges. And you are also going to have HSO4 minus as your counter anion. So this one's the conjugate base. And this one's the conjugate acid. Now this is not by any means favorable. This is the slow step of the reaction because you produced a carbocation. So it's not a very happy step. Now with the carbocation, and because this is a secondary carbocation in particular, you should be thinking to yourself, is there any possibility of a hydride or a methyl shift? Now, if you haven't gotten to the slides where I talk about that yet, don't be too concerned. We'll get there. But the point is, if you were to do a shift in this case, you could only make a primary carbocation. So there are no shifts in this particular case. It just isn't stable enough. And at this point, you need to have somebody add to the carbocation to make the situation happy again. Now, this reaction could go backwards. In other words, this oxygen of the hydrogen sulfate anion could pick off one of these protons that you just added and reform the double bond, but that's not productive chemistry. So we're not going to do that. That means we've got to have a nucleophile come in. You have two potential nucleophiles in this solution. One is water, because that's our solvent. And the other potential nucleophile is this hydrogen sulfate anion. Okay. The reason this is such a poor nucleophile, the hydrogen sulfate anion, is because it has resonance delocalization of its negative charge through all three of these oxygens attached to the sulfur. So I could draw two other structures. Now I know they're going to look exactly the same, but it's going to show the negative charge on a different oxygen atom. And that's the whole point. The fact that I can delocalize this negative charge onto a different oxygen means that that negative charge is not localized in only one location. It is delocalized, which is going to stabilize this anion. It's a very, very poor nucleophile because it has resonance delocalization of its negative charge. And I can draw all three resonance structures to describe this. It's also a minor component in the solution because we use dilute sulfuric acid. So for those reasons, water is the preferred nucleophile. Now I know it's not a great nucleophile. It doesn't have a negative charge. It does have two things going for it. It does have lone pair electrons, which nucleophiles must have, and it's highly abundant in the solution. It's the solvent. Okay, this is like air that we interact in. This is the solvent of this reaction. There is tons of water, so it's highly available. So even though it's not a good nucleophile, it can be a nucleophile. This hydrogen sulfate anion, on the other hand, has a delocalized negative charge. It's pathetic in terms of its ability to be a nucleophile. Absolutely pathetic. So it sits around and is a spectator ion for the rest of the reaction. That is why you want to use an oxyacid. It's because this corresponding conjugate base, after we've deprotonated the acid, is absolutely pathetic due to the fact that it has resonance delocalization of its negative charge. That makes it a terrible nucleophile, and it will not participate in the reaction any further. So at this point, we get to the fast step of the reaction. So we have here our carbocation that we formed in the previous step. And like we've mentioned previously, it needs to be able to stabilize itself. It needs to take care of the fact that it doesn't have an octet. It's got a positive charge. So water will be the electron pair donor. And we've seen this previously with the halides. Okay, they can also be nucleophiles. That's why you're not using an acid like HI, HBr, HCl, because their corresponding conjugate bases are decent nucleophiles. We want to make sure that that corresponding conjugate base has nothing to do with the rest of the reaction. That is why you're using an oxyacid. So oxygen is going to use its lone pair electrons and add to this carbocation. And as it does so, you will make an alkyl oxonium ion. Okay? I didn't draw out the methyl group before, but I did this time. It's okay. Anyway, you do produce this alkyl oxonium ion. Now, what we need to do for the oxygen, because it also doesn't like to be positively charged, is satisfy it in some manner by breaking either a bond between oxygen and carbon or a bond between oxygen and hydrogen. If you break the oxygen-carbon bond, you go right back where you were a moment ago. And that is a possibility. Absolutely, it's a possibility. But that's not productive chemistry. So what we want to do instead is break an oxygen-hydrogen bond. And you can do this either with the HSO4- or with water. Either one of these can be used. I'm going to use water because it's more prevalent in the solution. But you could get away with using either one and be perfectly fine in terms of your mechanism. The point is to regenerate the acid catalyst. So if you want to use HSO4- because it makes more sense to you, that is fine. I'm going to use water though because it does make a weaker acid in the course of the reaction. So oxygen here is acting as the base, picking up the proton, and the OH bond is broken, and oxygen gets the electrons because oxygen is more electronegative. In the end, what you've done here is you've created an alcohol. And you've regenerated the acid catalyst. Okay, those are spectators. But this is what we mean by a Markovnikov addition of water. The hydrogen adds to the less substituted carbon, and the OH group adds to the more substituted carbon of what was the alkene.